Hello everyone, welcome back to Calculus 1, and this time we are moving to a new section, section 3.8, implicit differentiation. If you ask me what is implicit differentiation, I really will have to tell you it is all about the chain rule. It is all about the chain rule, okay. So how about let's get started. And first, maybe you want to recall the power rule with the chain rule, or maybe we call this a general power rule. The derivative of a function relating to the power of r, it is r times f prime times f to the power of r minus 1. It's a little more complicated than the simple power rule, right? This is a general power rule, okay. The combination of power rule and the chain rule. And also, I hope you remember, usually when we have a function, instead of using f of x, we just use y. And we say y is a function of x. Or simply we write y as a function of x. So accordingly, does this make sense to you? The general power rule seemingly can be somewhat simplified. Derivative y to the r. And don't forget the dd notation, ddx, y to the r. Y is a function of x. So it will be r times y prime times y to the r minus 1. So this is just another way to write the general power rule. Keep in mind why it is assumed, it is implied as a function of x. The derivative we are calculating it is with respect to x. So accordingly, if you have any confusion about this way of writing, keep in mind why it is assumed, why it is implied as a function of x. So when r equals 1, d dx of y, which is dy dx, which is just y prime, well, like we did it many times. And then d dx of y squared, still keep in mind y is a function of x. So there's a chain rule involved, 2 to the y, and then times y prime. And when r equals 3, ddx of y x to the power of 3, it is 3y prime times y squared. General power rule. And then let's take a look. How do we find out this kind of weird thing, derivative of x squared times y cubed? And still, we do have the same assumption. Y is a function of x. Y is implied as a function of x. Okay, so this time I'm seeing pretty clear the derivative we are calculating, it is in a product form, right? So that's the reason what I said, well, why I said we needed to have the product rule. And also I have the formula copy and pasted. Derivative of u times v is u prime v plus uv prime. Certainly in this case, I hope you recognize u is x squared, v is y cubed, or maybe let me just write on a little more work. Let u, this is what I did, u is clearly u is x squared, and then v is y cubed. V is y cubed. And then accordingly, we can tell u prime. U prime, not a lot to explain. You got to know this very well. Well, u prime, it is just 2x, right? 2x. And the v prime, don't just rush to say it has to be 3y squared. V prime, it should be v prime, it has 3y squared. And then because the chain rule, there's a y prime in the end. And if you want, you could put a y prime in the middle. Okay, but anyway, I guess for the cases we are considering here, you usually put a y prime in the end, it's better. Okay. And then putting this in together, d dx of x squared y cubed, as I'm saying, I'm considering the product rule. U prime v, u v prime. And I really did not do a lot of simplification here. The first term stayed the same. I just moved the other 3 in the middle to the very front. So 3x squared plus y squared y prime. Now maybe I can give you some better idea about implicit differentiation. Usually it is under the situation y is implied as a function of x, and then when we calculate the process to calculate a derivative involving both x and y, and that process it is the implicit differentiation. Implicit differentiation. Really, it is all about the chain rule. It is all about the chain rule. How about let's work on some more examples. They are all from the textbook. Example 3.68, and indeed, this is the equation, and indeed, I suppose you know this equation is not complicated, right? It's the equation of circle, okay? And we want to find out dy dx. It's worth to mention we could find out dy dx using the explicit differentiation. But anyway, I hope you understand the way to solve for y or isolate y. It's going to generate two answers: positive root and a negative root. So which means really would require two rounds of calculations. Even though in this case it's not complicated, it is doable. But anyway, if possible, we may just want to consider one right. So this is in general how implicit differentiation works. You don't necessarily need to have an explicit formula. Like in this case, we are only having an implicit formula. What you can do here is you take a derivative both sides with respect to x. So d dx. I said the dd notation it is better because it says clearly we are taking derivative with respect to x. And also don't forget y indeed it is implied as a function of x. Okay. Take a derivative both sides with respect to x. So the left-hand side, the sum. So it is sum of derivatives. Derivative of x squared, no doubt. That's 2x. Derivative of y squared. There's a chain rule involved. And also I did this a moment ago. Derivative of y squared, it is 2y times y prime. Right? 2y times y prime. And then derivative right-hand side. Well, remember derivative constant. It is just 0, right? So the right-hand side is 0. And then take a look. What do we want to achieve? We want to find out y dy dx. dy dx, it is y prime, right? So from here, we can solve for y prime. Y prime, it is dy dx. And which also can be simplified to negative x over y. That is the derivative. Implicit differentiation, it is to find out the derivative implicitly. In the case y is implied as a function of x, and then the derivative may also involve both x and y. And such a process, it is implicit differentiation. Implicit differentiation. Okay. And how about, as I mentioned, this equation related circle, I think there are some other examples on the textbook really based on this example. Maybe I'm moving to 71 first, 371. Because really you see the equation is the same as the example we just finished. And this time we are asking the classical question, the equation of the tangent line here at the 3 point negative 3 and negative 4. This is the equation of circle. This point, it is in the second quadrant. So even without doing any actual calculation, I suppose you can see, you can visualize the same. The tangent line, it is going up, right? The slope has to be positive. Okay. So let's take a look if we can figure out the slope correctly. And according to the calculation in the example 3.68, okay, this is the derivative, negative x over y, and the slope, it is the derivative at that given point. So you plug in 3 for x, negative 4 for y. It turns to be negative 3 over negative 4, or simply it is 3/4. As I said earlier, the slope indeed, it is positive. Consider the case if it makes sense to you. Okay, this is the graph of circle. In the second quadrant, basically the tangent line will have to go up. This is how I see the circle. So indeed, the calculation confirms the tangent line, it is positive. The slope of the tangent line is positive, which means the tangent line, it is going up. And then the equation of the tangent line, I suppose you do know from now on, you do know the point slope form of line, y minus y naught, is slope times x minus x naught. Slope as calculated. The point, x naught, y naught, they are given here. Y minus -4, I simply put y plus 4 over here. So this is the equation of the tangent line. That is about implicit differentiation. I'm just going to continue because the next example, it is still related. Example 3.70, it is also from the textbook. It is really the continuation from the example 3.68 we just did. 70, it is the continuation from 68. And remember, in 68, we can calculate the dy dx. So 70, we are asking for d2y dx2. So what I'm seeing here is because the derivative it is just derived over here. And then if we continue to take the derivative with respect to x both sides, and that involves with another round of implicit differentiation, right? So the derivative y prime, it is y double prime. And the derivative of the right-hand side, which is negative x over y, negative x over y. I guess I really don't need this middle part anymore. I'm saying this is a quotient. This is a quotient. So I use the quotient rule to calculate the derivative of the right-hand side. I did keep the minus sign in the front. So this should be considered as u over v. U is x, v is y. So u prime v minus uv prime. V squared, it is the original denominator squared. And also, it turned out to be a complex fraction. And I skipped some work. I hope you will reach the sign. Still keep in mind, I do have the single minus in the front. And then what I'm saying here is for the next part, you can consider multiply y to the entire top and y to the entire bottom. So y times y is y squared. And then actually for this part, y is cancelled from denominator, which turns to be x squared minus minus plus. And then times y to the denominator, multiply y to the denominator, that's y cubed. And still we do have the minus in the front. So we do have the second order derivative in this fashion. Again, it is from the implicit differentiation. Implicit differentiation. We are in section 3.8. We are considering implicit differentiation, and in some way it is really not new at all. It is just continued discussion of the chain rule, believe it or not. And maybe we spend a little more time. Let's finish another example. And if I miss anything or if needed, do use the textbook or do let me know. We can revisit this problem again, okay? It's example 3.69. And we want to find out dy dx. And this time you take a quick look. It would be, I think it is impossible to find out the explicit formula for y here. So definitely, if you don't have an explicit formula for y, definitely you want to consider implicit differentiation. So I simply take a derivative both sides with respect to x. Maybe starting with the easy side, easy part first, the right-hand side. Derivative right-hand side, it's just 4, right? Derivative left-hand side, first of all, it is the sum of two terms. So it would be the sum of derivatives. So I simply change this y in the end, in the left to y prime. And then the first term, it is a product y. So the derivative with respect to x, you're going to use the product rule. U is x cubed. V is sine y. Keep in mind, y is implied as a function of x. So using the chain rule and the product rule, I get the derivative of this part, x cubed times sine y is 3x squared sine y plus x cubed. Sine y tends to be cosine y derivative rule. And don't forget there's another y prime in the end. Okay. And then look closely. For this problem, indeed, we need to have dy dx, which is just y prime. So what I did the next part is I have the terms y with y prime together, they are left to the left-hand side. And then the other term without y prime move to the right. And then for the left-hand side, y prime is a common factor. So I tried isolate this y prime. There's 1 plus x cubed times cosine y left. 1 plus x cubed, I think this part I missed something there. Should be not just y, it should be cosine y. Yeah, now I think I should be all right. Okay. All the examples, basically all the examples they are from the textbook. And I think I need to take a break for now. I cannot make the video too long. Otherwise, it's not possible for me to post it online. Hey, thank you for watching. I'll see you next time.